Every cosmology textbook, every documentary, every classroom in the world tells you the same thing, that the universe began 13.8 billion years ago in a blinding flash called the Big Bang. That is, strictly speaking, not true. The age itself is correct, measured to within a fraction of a percent by satellites like WMAP and the European Space Agency's Planck mission. What is actually wrong is the idea that the Big Bang was a beginning at all. Working with James Hartle in 1983 and publishing our result in Nuclear Physics B, I arrived at something far stranger, the conclusion that the universe is finite in age but has no beginning, no first moment, no boundary where time starts. If that sounds like a contradiction, good, because when you truly understand it, the way you think about everything changes. Most people, if pressed, will say something like, yes, there was a Big Bang, and they picture an explosion, something blowing outward into pre-existing darkness. And then they run straight into the question that has haunted every human being who has thought about it for more than 30 seconds, which is what came before, what caused the explosion, and what was there before there was anything. Because they have no answer, they assume physics has no answer either, that this is where knowledge ends and speculation begins. I want to show you why that assumption is mistaken, and why the answer is far more beautiful and far more unsettling than any creation story ever devised. For most of recorded history, the prevailing view among scientists, philosophers, and theologians alike held that the universe was eternal and essentially static. It had always existed, and it always would. The stars were fixed, and the cosmos was unchanging on the grand scale. There was even a simple observational puzzle that should have troubled people far more than it did, known as Olber's paradox. If the universe is infinite and eternal and filled with stars, then every line of sight should eventually land on the surface of a star, which means the night sky should not be dark. It should blaze with light in every direction, at every point. The fact that the sky between the stars is black tells you something enormously important, that the universe has not existed forever. But for centuries, almost nobody listened. Even Einstein, when he first formulated general relativity in 1915, believed in a static universe. His equations told him something quite different, that the universe should be either expanding or contracting, and that it could not simply sit still. But he found this so disturbing, so completely at odds with the prevailing wisdom, that he introduced an extra term into his field equations called the cosmological constant, lambda, specifically designed to force the universe to remain static. In hindsight, it was an extraordinary act of self-sabotage by the greatest physicist of his generation. Other people, though, were paying closer attention to what the mathematics was actually saying. In 1922, the Russian physicist Alexander Friedmann derived solutions to Einstein's equations, showing that the universe could be expanding. And then in 1927, a Belgian priest and physicist named Georges Lemaitre independently reached the same conclusion and went further. Lemaitre proposed that if the universe is expanding now, then tracing it backwards leads to what he called the primeval atom, a state of extraordinary compression from which everything emerged. That was the first serious scientific proposal for what we now call the Big Bang. Einstein's response was dismissive, and he reportedly told Lemaitre that his mathematics was correct, but his physics was atrocious. He was, of course, completely wrong about that. 2 years later, in 1929, Edwin Hubble settled the matter with observations at the Mount Wilson Observatory. Distant galaxies turned out to be moving away from us, and not just a few of them, but all of them, in every direction. The farther away a galaxy sat, the faster it receded, and this relationship, now known as Hubble's law, became the first direct observational evidence that the universe is expanding. Lemaitre had been right all along. Think about what that means. If everything is moving apart now, then in the past, everything was closer together. Run the clock backwards, and 1 billion years ago the universe was smaller, 5 billion years ago smaller still. Keep going, 10 billion years, 13 billion years, and the galaxies crowd together as the matter compresses and the temperature climbs. Push the equations all the way back, all the way, and you reach a point where all the matter and energy in the observable universe was compressed into a region of zero size. The equations produce infinities, infinite density, infinite temperature, infinite curvature of space-time, what physicists call a singularity, and that is really just a polite way of saying the equations have broken down completely. When your mathematics gives you infinity, that is not a triumph, it is a cry for help, the theory telling you it has reached the limits of its own understanding. That is the Big Bang. Not an explosion in space, but an expansion of space itself. The difference is critical, and it is one most people never fully absorb. When a bomb goes off, Debris flies outward through pre-existing space. But the Big Bang was nothing like that. Space itself came into existence, and time came into existence with it. There was no outside for anything to expand into, and there was no before in which a cause could operate, because time itself had no meaning at that point. None of this was just theoretical speculation. In the 1960s, Roger Penrose had done extraordinary work at the University of Oxford, showing that singularities are an inevitable consequence of general relativity in the context of collapsing stars and the formation of black holes. What I did, working with Penrose during my years at Cambridge in the Department of Applied Mathematics and Theoretical Physics, was turn that reasoning around. If singularities are inevitable when matter collapses inward, then they are equally inevitable when you trace the expansion of the universe backward. Together we proved a series of theorems, the Penrose-Hawking singularity theorems, demonstrating that under very general conditions, if general relativity is correct and the universe contains the amount of matter we observe, then space-time must have had a boundary in the past, a point where the theory itself collapses and time reaches its edge. That was not a minor result. It meant that the beginning of the universe was not an optional feature of cosmology. It was a prediction, a mathematical consequence of the best theory of gravity we possess. But here is where most popular accounts stop, right at the point where the story becomes truly interesting. Those singularity theorems relied entirely on classical general relativity, pure gravity with no quantum mechanics. And we know with certainty that at the Planck scale, at distances of 10 to the minus 35 meters and energies that existed only in the first 10 to the minus 43 seconds, quantum effects cannot be ignored. Classical general relativity, magnificent as it is, must break down at the singularity. The theory does not give a wrong answer. It gives no answer at all. The map does not merely become inaccurate, it goes completely blank. What we need is a quantum theory of gravity, a theory that unifies Einstein's general relativity with quantum mechanics. A complete theory of that kind does not yet exist, and it remains one of the great unsolved problems in physics. But progress can be made, and the progress we made led to what I consider one of the most extraordinary ideas in the history of the subject. Let me build up to it carefully. In quantum mechanics, there is a technique developed by Richard Feynman called the sum over histories, also known as the path integral formulation. In the classical picture, a particle travels along a single definite path from point A to point B, one trajectory, one history. In quantum mechanics, the particle takes every possible path simultaneously, and you have to add up the contributions from all possible histories, weighted by a quantity related to the action along each path, where the probability of any particular outcome is determined by this sum. Most of the paths cancel each other out through interference, and the ones that survive, the ones that actually contribute, cluster around what we would call the classical trajectory. That is how the ordinary, sensible world of our everyday experience emerges from the quantum world underneath. Applying this idea to the entire universe is, I should admit, an extraordinary leap. It means treating the geometry of all of space-time, every possible shape the universe could take, as a quantum variable. Most physicists, when they first encountered this proposal, thought it sounded mad. I understand the reaction, but the mathematics turned out to be well behaved in ways nobody expected. What James Hartle and I proposed was that instead of asking what the initial conditions of the universe were, instead of trying to specify the state of everything at the moment of the Big Bang, we should sum over all possible histories of the universe, every possible geometry of space-time, every possible way the cosmos could have evolved, and add them all up. This was our proposal for the wave function of the universe, a quantum mechanical description of the entire cosmos. But to make this sum mathematically well defined, we had to do something that sounds, at first, utterly bizarre, which was to use imaginary time. Let me explain what that means, because it is essential, and it is where most people's intuition fails them. In ordinary physics, time is measured by real numbers, 1 second, 2 seconds, 3 seconds. Imaginary time is measured in what mathematicians call imaginary numbers, multiples of the square root of -1. This is not mere mathematical trickery or just a computational convenience. When you replace real time with imaginary time in the equations of general relativity, a procedure known technically as Wick rotation that takes you into what physicists call Euclidean quantum gravity, something extraordinary happens. The distinction between time and space disappears entirely, and time becomes just another dimension of space. Instead of a space-time with 3 dimensions of space and 1 of time, you get a smooth, 4-dimensional space, a closed surface like the surface of a sphere but in 4 dimensions. And here is the key insight. Think about the surface of the Earth, which is finite, has a definite area, but has no boundary. There is no edge. You can walk in any direction, and you will never fall off, and you will never reach a wall with a sign that reads, "End of the Earth." For centuries, map makers drew edges on their maps and wrote, "Here be dragons." The conceptual revolution came when humanity accepted that the Earth's surface has no edge at all, that the surface is finite but boundless. The proposal Hartle and I made, the no-boundary proposal, states that the universe is like that. In imaginary time, the universe is finite in extent but has no boundary, no edge, no singularity, no point where the laws of physics break down, and no moment of creation where you have to appeal to something outside of science to set the initial conditions. Let me make this more concrete with an analogy I have used many times, including in A Brief History of Time. Consider the surface of the Earth again, but this time, think of lines of latitude as playing the role of imaginary time. As you travel south, the circles of latitude get smaller and smaller until, at the South Pole, the circle shrinks to a single point. But there is nothing special about the South Pole itself. It is just an ordinary point on the Earth's surface, governed by the same laws of geometry as every other point, with no boundary and no edge and no dragon. Now consider the question of what lies south of the South Pole. That question has no meaning. It is not that we lack the answer, it is that the question itself fails to make sense. Latitude simply does not extend beyond the South Pole, and south has no meaning at the southernmost point. That is exactly what the no-boundary proposal says about time. Time behaves like latitude on the surface of the Earth, and as you go back toward what we would call the beginning, time gradually becomes more space-like. Just as the circles of latitude become smaller near the pole, at the South Pole of the universe, time simply ceases to be a meaningful concept. There is no boundary and no edge and no moment before which you can ask what happened. The question of what came before the Big Bang is like asking what is south of the South Pole. It is not a question that has an answer we have not yet found. It is a question that carries no meaning at all. Stop and sit with that for a moment. If this picture is correct, and the mathematics supports it with striking elegance, then the universe did not begin with a singularity. It did not spring into being from some prior state, and it did not need a cause, because there was no time in which a cause could operate. The universe simply is. It has a finite past, but no beginning in the usual sense, no first moment, no boundary requiring an external explanation. In the language of information theory, the universe requires 0 bits of externally specified initial data, and it is, in the deepest sense we can articulate, entirely self-contained. That is, I believe, one of the deepest insights physics has ever produced. The universe can be finite in time and yet require no boundary conditions, no moment of creation, no need for a creator to set things going. The laws of physics are sufficient, on their own, to explain the existence of everything. I want to be precise about what I am claiming and what I am not. I am not saying we have proved the no-boundary proposal beyond all doubt, because it remains a proposal and a hypothesis. There have been serious challenges to it, including important work by Neil Turok and others, examining whether the Lorentzian path integral supports the same conclusions as the Euclidean one. These are legitimate scientific debates, and they are ongoing. What I am saying is that the no-boundary proposal stands as a consistent, mathematically rigorous hypothesis that answers what was previously thought to be an unanswerable question. The alternatives, a universe that is infinitely old or a universe that springs from an inexplicable singularity requiring conditions imposed from outside physics, carry far less explanatory power. Consider the steady-state theory, which once served as the main rival to the Big Bang. Fred Hoyle championed it, and the irony is that Hoyle himself coined the very term Big Bang as a form of mockery during a BBC radio broadcast in 1949. The theory held that the universe has no beginning and no end, that new matter is continuously created to maintain a constant density as the universe expands. It was an attractive idea, but evidence killed it. In 1965, Arno Penzias and Robert Wilson at Bell Labs in New Jersey were testing a horn-shaped radio antenna and could not eliminate a persistent background noise. They cleaned pigeon droppings from the dish, checked every connection, every joint, every component, and the noise would not go away. It was coming from everywhere in the sky, equally, in every direction. What they had stumbled upon, without intending to at all, was the cosmic microwave background radiation, the thermal afterglow of the early universe, a fossil imprinted on the sky from a time when the cosmos was incredibly hot and dense. If the universe had existed forever in a steady state, there would be no such signal, And its discovery told us with extraordinary confidence that the universe was once in a radically different state, that it has evolved, and that it has a history with a definite starting chapter. Hoyle's mockery ended up becoming the accepted name for the very thing that destroyed his theory. The second law of thermodynamics points in the same direction. If the universe had existed for an infinite time, it should have already reached thermodynamic equilibrium, what physicists sometimes call the heat death. Every part of the universe should rest at the same temperature. Every process that can occur should already have occurred. The stars should have burned out, and the black holes should have evaporated through what I described as Hawking radiation. Everything should have settled into a uniform, featureless haze of maximum entropy. The fact that none of this has happened, that there are still stars burning, still galaxies forming, still gradients driving the engine of complexity in life, tells us the universe has not been running forever. It has a finite age, and it had a beginning. And the evidence continues to accumulate with increasing precision. Measurements of the cosmic microwave background, first by NASA's COBE satellite, for which George Smoot and John Mather received the Nobel Prize in 2006, then by WMAP, and most recently by the Planck satellite, have given us an extraordinarily detailed portrait of the universe when it was only 380,000 years old. The patterns in that radiation, the tiny fluctuations in temperature from one point on the sky to another, match the predictions of inflationary Big Bang cosmology, the framework developed by Alan Guth and others, with astonishing precision. Those fluctuations are, in a very real sense, frozen sound waves, acoustic oscillations in the plasma of the early universe that physicists call baryon acoustic oscillations, now stretched across the entire sky. You are looking at the first sound the universe ever made, preserved in light. Here is the beautiful part. In the no-boundary proposal, these initial fluctuations, the seeds of all the galaxies and all the stars and all the planets and all of us, arise naturally from quantum mechanics. They are not imposed from outside, and they are not arbitrary initial conditions chosen by some external agent. They are a consequence of the quantum nature of gravity in the very early universe, which means the universe, in a sense, wrote its own blueprint. The seeds of complexity were woven into the fabric of space-time from the very start, or rather from the very South Pole, where time itself has no meaning, and the question of who or what chose the initial conditions dissolves along with the concept of initial. What I find most striking is what this means for the oldest question in philosophy, why there is something rather than nothing. If the no-boundary proposal is correct, then the universe has no external boundary at which conditions need to be specified, and it is entirely self-contained. The laws of physics, operating without any boundary conditions, produce the universe. That means the question of why the universe exists reduces to the question of why the laws of physics exist. And that, I admit freely, is a question I cannot answer. Perhaps no one can. But we have pushed the mystery back to its most fundamental possible form, and that, I think, is genuine progress. I wrote, at the end of A Brief History of Time, that if we discover a complete theory of the universe, it would be the ultimate triumph of human reason, for then we would know the mind of God. I should be clear about what I meant by that. I was not speaking of a personal deity. I was speaking of the deepest level of understanding available to any conscious being, the final set of laws from which everything follows, requiring nothing outside themselves. To know why the universe exists, why the laws are what they are, would be to understand something so fundamental that the phrase, the mind of God, is barely adequate to describe it. The universe had a beginning. The evidence is overwhelming, the mathematics is rigorous, and the implications are staggering. But the beginning was not what anyone expected. It was not an explosion in pre-existing space, and it was not a moment preceded by emptiness. It was not a first tick of a cosmic clock. It was something far more subtle, a boundary that is not a boundary, a beginning that is not a beginning, a point where time itself loses meaning, and the question of what came before dissolves into incoherence, the way south dissolves at the pole. That is what the origin of the universe really is, not a mystery beyond the reach of science, but a mystery science has answered, and the answer is stranger, more elegant, and more humbling than any story we ever told ourselves around a fire, looking up at the dark spaces between the stars, and wondering how it all began.